Look up at the night sky. What you see is just the beginning. Beyond those twinkling points of light lies a universe so vast, so strange, that it challenges everything we think we know about reality itself. For thousands of years, humans have gazed upward and wondered, are we alone? How did it all begin? What lies at the very edge of existence? Tonight, we journey to the frontiers of space and time, to places where the laws of physics bend and break, where matter disappears into nothingness, and where the universe itself was born in a flash of unimaginable violence. This is the story of humanity's greatest quest, the search for our cosmic origins, our place in the vast darkness, and the shocking discoveries that have rewritten the rules of reality. In 1609, Galileo Galilei pointed a simple telescope toward the heavens. What he saw changed everything. The moon was not smooth and perfect, but scarred with craters and mountains. Jupiter had its own moons, circling like a miniature solar system. The Milky Way, that ghostly band across the night sky, revealed itself as countless individual stars. For the first time, humans realized the universe was far larger than anyone had imagined. But Galileo's revelations were just the first whisper of a cosmic symphony that would take centuries to hear. 300 years later, in 1929, astronomer Edwin Hubble made a discovery that shattered our understanding of the cosmos. Using the most powerful telescope of his time, Hubble observed distant galaxies. But these weren't standing still. They were racing away from us at incredible speeds. The more distant the galaxy, the faster it was retreating. This could only mean one thing. The universe itself was expanding, growing larger with each passing moment. If the universe was expanding now, then in the past it must have been smaller. Much smaller. Rewind time far enough, and everything in the universe, all the matter and energy that exists today, would have been compressed into a single point. A point smaller than the head of a pin, but containing the seeds of everything that would ever be. Scientists called this moment the Big Bang, the birth of space and time itself. But if the Big Bang created everything, what came before it? And what lies beyond the edge of our expanding universe? These questions would drive the next century of space exploration and scientific discovery. The race to understand our cosmic origins began in earnest after World War II. In 1957, the Soviet Union launched Sputnik, humanity's first artificial satellite. A metal sphere no bigger than a beach ball, beeping its simple radio signal as it circled Earth. That beep changed the world. Suddenly, the space beyond our atmosphere wasn't just a place to observe. It was a destination. 4 years later, Soviet cosmonaut Yuri Gagarin became the first human to leave Earth's surface. His 108-minute orbit around our planet opened the door to an age of exploration unlike any in human history. The Americans followed quickly. Project Mercury, then Gemini, building toward the ultimate goal, the Moon. On July 20, 1969, Neil Armstrong stepped onto the lunar surface. His famous words, "That's one small step for man, one giant leap for mankind," marked humanity's first footsteps on another world. But the Apollo missions delivered more than national pride. They fundamentally changed how we see ourselves. The famous Earthrise photograph, taken by Apollo 8 astronaut William Anders, showed our blue marble planet rising above the moon's desolate horizon. For the first time, humans could see Earth as it truly is, a fragile oasis of life, suspended in the infinite black of space. Environmental scientist James Lovelock would later say, that image sparked the modern environmental movement. We finally understood that Earth is our only home in a universe that, as far as we knew, was utterly lifeless. But was it really lifeless? That question would soon become one of the most important in all of science. As the 1970s dawned, robotic explorers began venturing deeper into the solar system than any human had traveled. Pioneer 10 and 11 flew past Jupiter, revealing a world of violent storms and mysterious moons. The Viking missions landed on Mars in 1976, searching for signs of life on the red planet. They found a world that had once been warm and wet, with vast river valleys and ancient lake beds. But no life, at least none that our instruments could detect. The Voyager spacecraft, launched in 1977, embarked on humanity's greatest journey of discovery. These twin robots would visit Jupiter, Saturn, Uranus, and Neptune, transmitting images and data across billions of miles of space. The Voyager missions revealed wonders beyond imagination. Jupiter's moon Europa, covered in a shell of ice that might hide a liquid ocean beneath. Saturn's moon Titan, shrouded in thick atmosphere and dotted with lakes of liquid methane. Geysers of water erupting from Saturn's tiny moon Enceladus. Each discovery expanded our definition of where life might exist. But the most profound revelation was still to come. Hidden in the data from these early missions was a clue that would revolutionize our understanding of the universe itself. The 1990s brought a revolution in astronomy. New telescopes, more sensitive instruments, and most importantly, the Hubble Space Telescope, orbiting high above Earth's blurring atmosphere. Hubble could see farther and more clearly than any telescope before it, and what it saw posed a profound mystery. Scientists used Hubble to measure the expansion of the universe more precisely than ever before. They expected to find that the expansion was slowing down, gradually weakened by the gravitational pull of all the matter in the cosmos. Instead, they discovered something impossible. The expansion was accelerating, getting faster over time. This discovery won the 2011 Nobel Prize in Physics. But it also created a crisis in cosmology. What could possibly be driving the universe to expand at an ever-increasing rate? The answer, scientists realized, had to be some form of energy. An energy that filled all of space and pushed against gravity itself. They called it dark energy, and according to their calculations, it makes up nearly 70% of everything that exists. Dark energy was invisible, undetectable by any instrument we possessed. Yet it was the dominant force in the universe. But dark energy wasn't the only invisible component of the cosmos. In the 1970s, astronomer Vera Rubin made observations that challenged everything we thought we knew about galaxies. She studied the rotation of spiral galaxies like our own Milky Way, based on the visible matter, stars and gas clouds. These galaxies should have been spinning themselves apart. There simply wasn't enough gravitational pull to hold them together. But the galaxies remained intact. Something was providing the extra gravity needed to keep them stable. That something was invisible. Astronomers called it dark matter. Matter that doesn't emit, absorb, or reflect light, but whose gravitational effects are undeniable. Further studies revealed that dark matter makes up about 25% of the universe. Combined with dark energy, this meant that 95% of the cosmos consisted of things we couldn't see or directly detect. Everything we could observe, every star, planet, and galaxy, all the matter that makes up you and me, represents less than 5% of reality. We were living in a universe that was almost entirely invisible. This realization was both humbling and terrifying. How could we hope to understand a cosmos that was 95% hidden from us? Meanwhile, the search for life beyond Earth continued, but it was plagued by paradox and disappointment. In 1961, astronomer Frank Drake had proposed an equation to estimate how many communicating civilizations might exist in our galaxy. The Drake equation considered factors like the rate of star formation, the fraction of stars with planets, and the likelihood that life would evolve intelligence and technology. Even conservative estimates suggested there should be thousands, possibly millions, of technological civilizations in the Milky Way alone. So where were they? This question became known as the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" If the galaxy was teeming with intelligent life, we should have detected radio signals, visited by alien spacecraft, or at least found some evidence of their existence. Instead, we found silence. A universe that seemed empty of intelligence, except for our own small planet. The search intensified in the 1990s, with the discovery of the first planets orbiting other stars. These exoplanets, as they're called, came as a shock. The first ones discovered were nothing like the planets in our solar system. Hot Jupiters, giant gas planets orbiting closer to their stars than Mercury orbits our Sun. Super-Earths, rocky worlds several times more massive than our own planet. Planets with backwards orbits, planets in binary star systems, planets made of diamond. The universe of planets was far stranger and more diverse than anyone had imagined. By 2009, NASA's Kepler Space Telescope began a systematic search for Earth-like worlds. Over the course of its mission, Kepler discovered thousands of planets, including many in the habitable zone around their stars. The habitable zone, sometimes called the Goldilocks zone, is the region around a star where liquid water could exist on a planet's surface. Not too hot, not too cold, but just right for life as we know it. Kepler's discoveries suggested that Earth-like planets might be common in the universe. Perhaps 1 in 5 Sun-like stars hosts a potentially habitable world. With billions of stars in our galaxy alone, this meant billions of worlds where life might exist. Yet still, we found no signals, no signs of intelligence beyond Earth. The Fermi paradox deepened. As the 21st century progressed, new telescopes revealed even more cosmic mysteries. In 2003, NASA's Spitzer Space Telescope detected infrared light from some of the most distant galaxies ever observed. These galaxies existed when the universe was less than 1 billion years old. According to our models of cosmic evolution, such large, mature galaxies shouldn't have had time to form so early in the universe's history. Yet there they were, fully formed and massive, challenging our understanding of how structure emerges from the primordial cosmos. The James Webb Space Telescope, launched in 2021, pushed even further into the past. Its incredibly sensitive infrared instruments could peer through cosmic dust and observe the very first stars and galaxies to form after the Big Bang. What Webb found was astonishing. Galaxies that were larger, more massive, and more organized than theory predicted. Stars that formed faster and earlier than models suggested possible. It was as if the early universe was in a hurry to create complexity. But Webb also detected something else in those ancient galaxies. The spectral signatures of heavy elements like carbon, oxygen, and iron. These elements are forged in the nuclear furnaces of massive stars. When those stars explode as supernovas, they scatter these essential elements throughout space. Webb was seeing the chemical enrichment of the cosmos, happening much earlier than expected. The building blocks of planets and life were being distributed throughout the universe within the first few 100 million years after the Big Bang. This discovery had profound implications for the possibility of life elsewhere in the cosmos. Back in our own solar system, robotic explorers were making discoveries that revolutionized our understanding of where life might exist. In 2005, NASA's Cassini spacecraft detected water vapor and organic compounds erupting from the south pole of Saturn's moon Enceladus. This tiny, frozen world was geologically active, powered by tidal forces from Saturn's gravity. Beneath its icy crust lay a global ocean, warmer and saltier than Earth's polar seas. Similar discoveries followed. Jupiter's moon Europa almost certainly harbors an ocean beneath its ice shell. So do Ganymede, Callisto, and possibly Titan. Even more surprising, these subsurface oceans might be more common in the universe than worlds with surface water like Earth. Around red dwarf stars, the most common type of star in the galaxy, planets in the habitable zone would be tidally locked. One side permanently facing the star, the other in eternal darkness. Such worlds might be frozen on the surface, but tidal heating could maintain liquid water oceans beneath thick ice shells. Suddenly, the number of potentially habitable worlds in the universe expanded dramatically. But this created another paradox. If habitable environments are so common, why haven't we found life? The answer might lie in understanding the violence and chaos that characterized the early universe and continues to threaten life today. Gamma-ray bursts are the most powerful explosions in the cosmos since the Big Bang. These events, caused by the collapse of massive stars or the collision of neutron stars, release more energy in seconds than our Sun will produce in its entire 10 billion-year lifetime. A gamma-ray burst within a few thousand light-years of Earth could strip away our ozone layer, exposing the surface to deadly radiation and triggering a mass extinction. In the early universe, when stars formed and died more rapidly, gamma-ray bursts would have been far more common. Any planet that developed life might have seen it wiped out by these cosmic catastrophes. Supernovas, while less energetic than gamma-ray bursts, are more frequent and can sterilize entire regions of a galaxy. Then there are supermassive black holes. Every large galaxy, including our own Milky Way, contains a monster black hole at its center, millions or billions of times more massive than our Sun. When these black holes feed on surrounding matter, they can unleash jets of high-energy particles that travel at nearly the speed of light. Any planet caught in the path of these jets would be bathed in lethal radiation. The universe, it turns out, is a dangerous place for life. But perhaps the greatest threat to life in the cosmos is time itself. The universe is 13.8 billion years old. Our Sun is about 4.6 billion years old. Life on Earth appeared roughly 3.8 billion years ago, but complex life with nucleated cells, only evolved about 2 billion years ago. Intelligent life, capable of technology and space travel, has existed for less than 1 million years. Industrial civilization is barely 200 years old. This suggests that the evolution of intelligence might require billions of years and incredibly specific conditions. But the universe won't remain hospitable to life forever. Red dwarf stars, which make up about 75% of all stars, can burn for trillions of years. But Sun-like stars have much shorter lifetimes. In about 5 billion years, our Sun will exhaust the hydrogen fuel in its core and begin expanding into a red giant star. Earth's oceans will boil away, and our planet will become uninhabitable. Most stars in the universe more massive than our Sun will die much sooner. Even if life evolves on billions of worlds, most of it might never have time to develop intelligence before its host star dies. The window for intelligent life in the cosmos might be narrower than we thought. But there's an even more fundamental threat to life in the universe: the accelerating expansion driven by dark energy. As dark energy pushes the universe to expand faster and faster, galaxies are racing away from each other at ever-increasing speeds. Eventually, They'll be moving apart so quickly that light from distant galaxies will no longer be able to reach us. The observable universe will shrink, leaving each galaxy isolated in an expanding bubble of darkness. Within our own galaxy, star formation will gradually slow as gas and dust are used up, or heated beyond the point where new stars can form. Existing stars will age and die. White dwarfs will cool to black dwarfs. Neutron stars will slowly spin down. Even black holes will eventually evaporate through a process called Hawking radiation. In the far future, perhaps 10 to the 100th power years from now, the universe will be cold, dark, and empty. No stars, no planets, no life. This cosmic story has a beginning, the Big Bang, but it also seems to have an ending. Heat death, the gradual decay of all order and energy in the universe. If this is the ultimate fate of the cosmos, what does it mean for life, for consciousness, for everything we value? Is the universe fundamentally hostile to the emergence and persistence of intelligence? Are we just a temporary accident in a cosmos destined for eternal darkness? But perhaps our perspective has been too narrow, too focused on the threats and limitations, and not enough on the extraordinary nature of what we've already discovered. Consider this: in just 400 years, since Galileo first turned a telescope skyward, we've mapped the structure of the observable universe. We've traced cosmic history back to the first moments after the Big Bang. We've discovered thousands of worlds orbiting distant stars. We've landed robots on Mars, flown spacecraft past every planet in our solar system, and sent probes into interstellar space. We've decoded the cosmic microwave background radiation, the afterglow of creation itself, and used it to understand the fundamental properties of space and time. We've detected gravitational waves, ripples in the fabric of reality caused by colliding black holes billions of light years away. In the span of a few human lifetimes, we've gone from not knowing that other galaxies exist to mapping the large-scale structure of the entire cosmos. This is perhaps the most remarkable achievement in the history of any species on any world. And we're just getting started. The James Webb Space Telescope is revolutionizing our understanding of the early universe, planetary formation, and the potential for life beyond Earth. Ground-based telescopes are becoming more powerful and sophisticated. The extremely large telescope, currently under construction in Chile, will have a mirror 39 meters across, allowing us to directly image Earth, like planets around nearby stars, and analyze their atmospheres for signs of life. Space-based missions are being planned that will map dark matter throughout the cosmos, study the mysterious properties of dark energy, and search for the subtle signatures of life in the atmospheres of distant worlds. The search for extraterrestrial intelligence is expanding beyond radio signals to look for artificial lights on the night sides of distant planets. Megastructures around stars and other technological signatures of advanced civilizations. Private companies are joining government space agencies in pushing the boundaries of exploration. Reusable rockets are making space access cheaper and more routine. Humans are preparing to return to the moon, establish permanent bases there, and eventually journey to Mars. Within the next few decades, we may answer some of the most profound questions ever asked. Are we alone in the universe? What is the nature of dark matter and dark energy? How did the first stars and galaxies form? But perhaps the most important realization is this: we are not separate from the cosmos. We are part of it. Every atom in your body was forged in the nuclear furnace of a star. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was created in stellar cores and scattered into space by supernovas. Carl Sagan was right when he said we are made of star stuff. We are the universe becoming aware of itself. In developing science and technology, in exploring space and seeking other life, we are carrying out the cosmos' own quest for understanding. The universe spent 13.8 billion years evolving from a hot, dense state to a realm of galaxies, stars, and planets. On at least one of those planets, matter organized itself into living systems. Those systems evolved for billions of years, until they developed brains capable of contemplating the very cosmos that created them. We are the universe's way of asking questions about itself. This perspective transforms the cosmic challenges we face from depressing inevitabilities into urgent motivations. Yes, the universe can be hostile to life. Gamma ray bursts, supernovas, asteroid impacts, and climate change all threaten our existence. But we're developing the knowledge and technology to protect ourselves from these threats. We're learning to deflect asteroids, survive in space, and potentially even travel to other star systems. Yes, our sun will eventually die, and the universe may face heat death in the far future. But we have billions of years to develop solutions, to spread life throughout the galaxy, to find ways to survive the death of stars, and perhaps even create new universes. The challenges are immense, but so is our potential. We've gone from stone tools to space travel in just a few thousand years. Who can say what we might accomplish, given billions of years of continued development? The search for life beyond Earth continues with new urgency and new tools. Every month brings discoveries of new exoplanets, some of them tantalizingly Earth-like. The recently discovered TRAPPIST-1 system contains 7 Earth-sized planets, 3 of them in the habitable zone around their red dwarf star. Proxima Centauri b, the closest exoplanet to Earth, orbits in the habitable zone of our nearest stellar neighbor, just 4.2 light-years away. These worlds are close enough that we might be able to study their atmospheres with next-generation telescopes, looking for water vapor, oxygen, and other potential biosignatures. If we find evidence of life on nearby planets, it would suggest that life is common throughout the cosmos. That we are not alone, just isolated by the vast distances between stars. And if life is common, intelligence might be as well. Perhaps the reason we haven't detected alien civilizations yet is simply that space is enormous and our search has only just begun. Recent discoveries in our own solar system are also expanding the possibilities for life. Beneath the icy surface of Jupiter's moon Europa lies an ocean with more than twice as much water as all of Earth's oceans combined. NASA's upcoming Europa Clipper mission will fly by this moon dozens of times, using ice-penetrating radar to map the ocean and analyze plumes of water erupting from the surface. If Europa harbors life, it would demonstrate that biology can thrive in environments completely different from Earth's surface. Similar missions are being planned for Saturn's moon Enceladus and other potentially habitable moons in the outer solar system. We may discover that our solar system alone contains multiple independent origins of life. But perhaps the most profound implication of recent cosmic discoveries is what they tell us about the nature of existence itself. The cosmic microwave background radiation, the afterglow of the Big Bang, shows tiny temperature fluctuations that represent the seeds of all structure in the universe. These fluctuations follow the predictions of quantum mechanics. They appear to be random quantum events, blown up to cosmic proportions by the rapid expansion of space in the universe's first moments. This suggests that everything we see around us, from galaxies to stars to planets to life itself, ultimately emerged from quantum uncertainty. The deepest foundation of reality appears to be probabilistic, not deterministic. We live in a cosmos where chance and necessity dance together to create unimaginable complexity and beauty. The detection of gravitational waves has opened an entirely new window on the universe. These ripples in space, time itself, allow us to observe cosmic events that are invisible to traditional telescopes. We've detected the collisions of black holes billions of light years away, events so violent they shake the very fabric of reality. We've observed the merger of neutron stars, witnessing the cosmic forge where elements like gold and platinum are created. Soon, space-based gravitational wave detectors will be sensitive enough to observe the gravitational wave background, the cumulative signal from all the violent events in the universe's history. This may allow us to peer further back in time than ever before, perhaps even to the moments immediately after the Big Bang itself. As our exploration of the cosmos continues, we're beginning to understand our place in the vast sweep of cosmic evolution. We exist at a special moment in cosmic history, late enough for heavy elements to have been distributed throughout the universe, allowing for rocky planets and complex chemistry. Early enough that stars are still forming, and the universe is still rich with energy and possibility. We are the product of 13.8 billion years of cosmic evolution. But we may also be the key to the universe's future. Through science and exploration, we're extending the reach of consciousness throughout the solar system, and eventually to the stars beyond. We're transforming from a single planet species into a spacefaring civilization. Every step we take into space, every world we explore, every mystery we solve, is consciousness expanding its presence in the cosmos. The ultimate questions remain open. What came before the Big Bang? What lies beyond the edge of the observable universe? Are there other universes with different physical laws? Is consciousness a rare accident, or a fundamental feature of reality that emerges wherever conditions allow? Will we find other intelligences among the stars? Or will we discover that consciousness is so rare and precious that we may be the only minds capable of contemplating the cosmos? These questions may take centuries or millennia to answer fully, but the journey of discovery is as important as the destination. With each new telescope, each space mission, each scientific breakthrough, we're writing the greatest story ever told. The story of the universe coming to know itself. Look up at the night sky once more. Those points of light are no longer just distant suns, but entire worlds of possibility. Some of them may harbor life. Some may have witnessed the birth and death of civilizations. Some may be the future homes of humanity as we spread throughout the galaxy. The darkness between the stars is not empty, but filled with dark matter and dark energy, mysterious components of reality that we're only beginning to understand. That darkness is also filled with possibility, with worlds yet to be discovered, life yet to be found, and questions yet to be asked. We stand at the threshold of becoming a truly cosmic species, not just inhabitants of Earth, but citizens of the universe itself. The cosmos that gave birth to us through 13.8 billion years of evolution is vast beyond imagination. It contains mysteries that will challenge us for thousands of generations to come. But it also contains unlimited potential for growth, discovery, and wonder. We are made of star stuff, and we are returning to the stars. In doing so, we carry with us the accumulated wisdom of our species, the hopes and dreams of all who came before us, and the responsibility to preserve and spread the precious flame of consciousness throughout the cosmos. The universe is not just our home, it is our destiny. and our greatest adventures have only just begun.